Hello everyone! This video will be all about collision detection. Collision detection is very useful in video games. Basic things such as item collection, player damage, and most importantly solid objects wouldn't be possible without it. It can also be useful for other types of programs, especially ones that involve real-world simulations. There are many possible collision detection methods, and the one a program actually uses mainly depends on what shapes are being checked, as well as how precise the calculations need to be. In this video, I'll be focusing on broad versus narrow collision detection, and then explaining two of the narrow phase methods in more detail. Broad phase collision detection refers to methods that are very fast, but also a lot less precise. You can then probably guess that narrow phase collision detection methods are the opposite. The reason for this distinction is centered around performance. There's no need to run precise calculations on a pair of objects when you can easily tell that they're on opposite sides of the screen. So, that's the job of broad phase collision detection, to work out which objects are close enough to actually warrant a more precise check. There are many methods of doing broad collision detection, and I don't really plan to go into detail about them here. I just want to at least mention that there's usually other methods at play, aside from the two that'll precede this. Once broad phase collision detection is complete, and you've determined which shapes are close to each other, the program can then check if they're actually colliding. AABB stands for Axis Aligned Bounding Boxes, and it's the simpler method out of the two I'm going to talk about. AABB is decently limited because it only works on non-rotated rectangles. This is actually where it gets its name from. Axis aligned means, well, aligned to the axis, which is another way of saying non-rotated. And bounding boxes refers to the rectangular nature of the shapes. The calculations for AABB are based on the edges of the two rectangles. Basically, if you can prove that no gap exists between the sides of the two rectangles, then you know that they're overlapping. To understand how a computer might work through this, let's break down these two rectangles into their left and right bounds. I'll label the left bounds L and the right bounds R. Take note of their arrangement when there's a gap between the rectangles. When read from left to right, the order of the bounds is left, right, left, right. However, if I move the rectangles on top of each other, the center left and right bounds switch places. The order is now left, left, right, right. So basically, if both of the left bounds are to the left of both of the right bounds, then you know that there's no horizontal gap between the shapes. Since the computer should already know the coordinates of the rectangle's corners, it can simply use the x-coordinates of the sides to work this out. That might seem like it's all, but there is one additional nuance to this. You might notice I specified that we're checking the x-coordinates only. This is because we need to actually do two of these checks, one for the x-coordinates and one for the y-coordinates. It's only if the rectangles are overlapping on both the x-axis and the y-axis that they're actually overlapping. The reason for this becomes more clear if I show it like this. You can see that even though these rectangles are overlapping on the x-axis, there's still a gap between them along the y-axis, and therefore, there's no overlap. Once the gap along the y-axis is removed, however, you can now see that they're actually overlapping. I think that's enough coverage of AABB, so now let's move on to its big brother. You probably remember that AABB only worked on non-rotated rectangles. Well, the good news is that SAT works on any convex shape, regardless of rotation or side count. It even works on non-regular polygons. Before going over the math, I found a Stack Overflow post with an analogy for how SAT works that I thought was really good. Basically, imagine there are two objects, and we want to check whether they're touching. Let's also pretend that these objects are prisms in 3D space, and you're observing both of them from the side. You start out by observing the objects from one angle. They might look like they're touching from this angle, but as you move around the objects, let's say you eventually find that a gap does indeed exist between them. You can then conclude that they're not touching and move on with your life. However, if you couldn't find a gap between them, no matter which direction you looked at it from, then you conclude that they are touching. This is at the heart of how SAT works, by examining the objects from multiple angles to see if there's a gap between them. This is actually where SAT gets its name from. It stands for Separating Axis Theorem, which refers to the separating of the shapes into their components for each axis. Since SAT requires looking at the shape from multiple angles, you might be wondering how many of these angles need to be checked. The rule is that for every side on either shape, you examine the shapes from the angle that's parallel to that side. Here's an example of what I mean by that. If one of the shapes was this triangle, then we need to examine the shapes from this angle, and this angle, since they're all parallel to a side of the triangle. Once we have determined which angles we need to examine the shapes from, we can check each of those angles for an overlap. This is a process that's a little out of the scope of this video, and it mainly involves vector projections. Its job is to essentially squish the shapes onto a line that's at the angle we want to check, and then see if the squished versions of the shapes are touching. If they are touching, then there's an overlap at that angle, but if not, then there isn't an overlap. If the program finds a gap between any of the pairs of lines, then it knows that they aren't colliding, just like in the analogy I used earlier. However, if it iterates over every angle without finding a gap, then it can be certain that they are in fact colliding. Before the end of the video, I'd like to at least mention how solid objects work. At this point, we know how to check if two objects are overlapping, but what if we want the objects to actually repel each other? The answer to this is actually very simple, and it requires pushing the objects out of each other, which should make sense. The rule is that you push the objects out of each other away from the center along whichever axis had the least overlap. In AABB, since there are only two axes to consider, the object will either be pushed out horizontally or vertically. In SAT, it can be pushed along any direction perpendicular to a side of one of the shapes. The only remaining question is how much each of the two objects should budge. In simple games, you'll usually just have a static and dynamic object. The static object is something immovable, like a solid block, and the dynamic object is the object in motion, which is usually the player or some kind of enemy. More complicated physics engines, on the other hand, can allow you to assign a mass to each object, which will allow both objects to move a different amount. With that sums up everything I wanted to say about collision detection. There are a few additional links in the description if you want to check them out. One of them is an interactive simulation I made, and there's also the sources I used if you want some further reading. But anyway, that's how collision detection works, so cue the end screen.